Hi Math 215 students. In this second video for section 1.7, we're going to talk about why we might care about the idea of linear independence. The only outcome we want to cover in this video is to describe what connection exists between a set being linearly dependent and whether or not a vector is in the set is a linear combination of the others. Now, this outcome was actually touched on in the last video, and that's where we're going to start today. We're going to be giving you a couple reasons why looking at linear independence is interesting to us. We'll give a couple today, but there are many, many more reasons to come, especially as we get into ideas from Chapter 2 and Chapter 3. In particular, as you look at what we call the invertible matrix theorem, you'll see a lot of these same ideas sort of come to the forefront again. All right, so what we said in the last video was this theorem. A set of two or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. These were the examples we had in that last video of linearly dependent sets. And for each of these, you could see that for instance, the 0 vector is a linear combination of 1, 5, and 2, 7. 5, 6 is a linear combination of 1, 2, 3, 4, although we would have to do some work to figure out exactly which linear combination it is. And -4, -12, 20 is just minus 4/3 times the first vector, so it is a linear combination of the previous vector. Now, this idea about being able to write a vector from the set as a linear combination of the others when it's linearly dependent gives us two reasons why linearly independent sets are interesting, or from the other hand, linearly dependent sets. Our first reason has to do with redundancy in our vector set. And particularly, we want to talk about redundancy when it comes to span. So you'll remember the span of a set of vectors is the set of all the vectors that are reachable or creatable by taking linear combinations of the vectors in the set. So I've got two different sets here. The first set is a linearly independent set, and the second set is a linearly dependent set. If you want some practice, you could pause the video here and prove to yourself that that is the case, but we're just going to take it as given. And we're going to take a look at the spans of these two sets. Now, for the first set, which is a set of linearly independent vectors, you'll notice that we have two vectors that are sort of poking up above the xy plane. That's the gray shaded portion. And we have a third vector, which is pointed below the xy plane. It's pointing in kind of a different direction. Now, remember, when you form a linear combination of these vectors, it's like you're taking steps along the directions of these vectors and adding your vectors together. So if I were to pick a point, any point in three-dimensional space, I might take some of this vector, I might take some of these two vectors and add it together, and I would get the point I was interested in. And in fact, because these vectors are pointed the ways they are, we know that the span is going to be all of R3. Now, as we take a look at the second example, this linearly dependent set, if we were to draw these three vectors as well, we'll have things shown here. You'll notice that, for instance, -2, -6, 10 is that long vector pointed upwards, and 3, 9, -15 is located below the xy plane, and 4, -8, 4 is kind of shortened in this perspective. It's actually pointing more towards the viewer. Now, we have a depiction of this set. You'll notice we've got our three vectors, 4, -8, 4, 3, 9, -15, -2, -6, and 10. And if I were to rotate around, you kind of get a sense of how these vectors are situated in three-dimensional space. One thing you'll notice, though, as we do rotate around, is that this vector, -2, -6, +10, is pointing in the exact opposite direction as the vector 3, 9, negative 15. And as you compare the numbers, you'll see that that's because this vector is a negative 2/3 times this vector. This vector is a scalar multiple of that vector. And because it's negative and because it is a scalar multiple, we do get an arrow pointing in the exact opposite direction. And these two vectors together point along a single line. Now, if we were to look even more closely, we'll be able to see that these three vectors all lie on a single plane. And that means that if I were to look at linear combinations of those three vectors, I can certainly put them together, them and their opposite directions, to get to anywhere on that plane. But I will not be able to get to anywhere that is off of that plane. And so jumping back to the slide, displaying that plane in there, you'll see that the span of three vectors that are linearly dependent doesn't give you all of three-dimensional space. It only gives you part of three-dimensional space. In this particular case, it gives you the plane that was shown there. And that's going to happen every time you're dealing with linearly independent or dependent sets. A linearly independent set spans a space equal to the number of vectors in there. So we'll get all of our three-dimensional space by taking these three vectors. Each vector allows us to travel in a direction that the other two alone do not. On the other hand, when you have a linearly dependent set, because one vector is always a linear combination of the others, that means that the span won't include anything new if you were to throw that vector in there. What you'll get is exactly the same span you had before, and in that sense, one of those vectors is redundant and doesn't give you the full possibility of spanning. All right, now let's take a look at a second reason why there's a difference between linearly independent and dependent sets that we might care about. Linearly independent sets allow for a unique linear combination for each vector in the span. Let me illustrate this with an example. We're going to take the vector 7, 1, minus 11 and write it as a linear combination using both of the two sets we saw before. I'll remind you that the first one was linearly independent and the second one was linearly dependent. Now if I start with the first one and I try to write 7, 1, negative 1 as a linear combination, of course I can, because we saw geometrically that these three vectors span all of R3. And so what I would do to find the coefficients I want, I would take these three vectors and put them as columns of a matrix, of an augmented matrix, and write 7, 1, negative 1 as the last column. And if I can row reduce this, I'll find out what should be the coefficient on each of these vectors to produce the result of 7, 1, negative 1. So skipping ahead, I'm going to do a row reduction. We'll put this in reduced echelon form. I actually used Octave to help me do this. We may talk a little bit more about Octave shortly. But these are the coefficients that I came up with for the coefficient on the first vector, the second vector, and the third vector. And that means that 7, 1, minus 11 can be written with this particular choice of coefficients. Now there is a little bit of round off error which you might see if you actually do this computation. But in principle, these decimal places, if they were allowed to expand out forever, they would give you an exact way of writing 7, 1, minus 11 as a linear combination of these vectors. And what's important is that in this process, along a row reduction, we found that there are three pivot positions, one in each row, one in each of these first three columns, which means that none of these columns is, none of these coefficients is a free variable. In fact, there is only one solution to this system. Now let's compare that to the second set of vectors. Now in the second set of vectors, the linearly dependent set, let's take a look at that same problem of writing 7, 1, minus 11. Now one thing we might worry about is whether this is even in the span of these three vectors, but it turns out that it is, and we don't have to go through this process. We can actually see that 7, 1, minus 11 is, if we just happen to add the first two vectors together, and we'll see that actually 7, 1, minus 11 is the sum of the first two vectors. Now what's interesting though is that because the third vector is negative 2/3 times the second vector, if I wanted to, I could replace the 3, 9, negative 15 by minus 3/2 times negative 2, negative 6, and 10, because that is the same as the middle vector. And in general, what this leads to then is that we get more than one choice of coefficients for these three vectors that will allow us to create that other vector in the span. This is in contrast to this situation where there was exactly one solution to which coefficients you should use. Now actually there are multiple solutions to the coefficients we could use. More than one possible linear combination will produce the 7, 1, minus 11. Now, this may not be the most exciting of lists, but those are two first reasons why linear independence is kind of a neat idea. They're both related to the span of the vectors involved. Linearly dependent sets have redundant vectors when it comes to their spans, and the linearly independent sets allow for a unique linear combination for each vector in the span. These properties will show up again. We're going to talk about related ideas in chapters 2 and chapter 3, and we'll culminate when we talk about the bases of vector spaces, which will happen in chapter 4. So stay tuned for that. Take another look at the outcome. You want to be able to describe the connection between a set being linearly dependent and whether or not a vector in the set is a linear combination of the others. Hopefully you can do that. If you have any questions, please let me know, and I will see you in the next video.